Next, I want to illustrate the importance of properly determining whether a variable you're trying to use as a predictor is supposed to be categorical or continuous. You will be inappropriately interpreting your results if you get it wrong in either direction. So in order to show that it's inappropriate to take a continuous variable and handle it as categorical, I'm going to focus on a variable we haven't focused on too much yet in this discussion. So this is the REM sleep variable, and I'll summarize it here. You can see that it's NA for 22 of the animals in this data set. So we're gonna allow some rows to drop as we go through this small part of the tutorial. That's fine. Those 22 rows will drop out, and I don't have any compelling reason to deal with that here because we're not trying to actually interpret these models. We're just trying to illustrate how regression and ANOVA relate. So okay, you can see this is a continuous variable, right? You can take the mean of it, etc. We can make a box plot of REM sleep, and we can see that it has a particular distribution. Nothing shocking here. Make a plot where the x-axis will be REM sleep and the y-axis will be log sleep. You can see that perhaps we should think about logging REM sleep. I'm not going to bother here because I'm not trying to actually fit this model, but certainly there's a relationship between the amount of REM sleep and the total amount of sleep, which should not be something that's shocking. Okay, so I'm going to run a regression of log sleep on REM sleep, and I'm going to run the ANOVA as well. These are both the same models, but I want to show you both the regression and ANOVA output. Remember that REM sleep is a continuous variable. Okay, so here's the output from the linear model. I've got estimates of my coefficients. So if I fit a line to this pattern that I see here, even though a line might not be appropriate, if I were to fit a line, its intercept would be 1.7 and its slope would be about 0.3, and we have tests for whether each of those is significantly different than 0. They both do appear to be significant, which makes sense. And we have the usual things, and it's nice that we have a reminder that observations are deleted. That's good to see. We have a residual standard error, we have our multiplier squared, we have our f-statistic, and then if we look at the ANOVA output, this is exactly parallel to the example that we talked about before when we used just one continuous predictor of log weight. Because REM is continuous, degrees of freedom is equal to 1, so that's a place to check that we really are dealing with this as a continuous variable. We'd have that 1 there. This p-value here is identical to this p-value here because they're the same test, and you see the p-value again here. This is also the same test. So again, this is exactly the same thing that we illustrated earlier when we had just one continuous predictor. What happens if either accidentally or because I'm confused, I handle this as a factor? So in other words, I think that each possible value of REM sleep is actually a different categorical level. So if I make a box plot of log sleep by all the different possible values of REM sleep, so I make this a factor variable, I can see the same pattern that I saw before. And in fact, I like this kind of plot because this is how I like to think about regression. For each value of the predictor, what's the distribution of the outcome variable? So this is what we see here. But what if we incorrectly use this predictor as a categorical predictor? We're not going to be taking into account the fact that as REM sleep increases, there's some particular way that log of sleep increases. Rather, we're going to be thinking about each of these box plots as a separate entity with no particular ordering to them. So if I run the linear model and also the ANOVA, because it's the same model, just with different default output of log sleep on the factor version of REM sleep, I should be able to tell immediately that something went wrong. So it's important that you know how to identify a situation like this. Looking at the regression output, what we see happened is that because REM sleep was handled as a categorical variable, we have coefficients for all but one of the different possible values of REM sleep. So this row here gives us the coefficient for the indicator that REM sleep is equal to 0.4. This right here is a coefficient for the indicator that REM sleep is equal to 0.5, a coefficient for the indicator that it's equal to 0.6, etc. So now for every value of REM sleep that occurred in the data set, except for one baseline value, I have a different coefficient that I'm estimating. So there are occasions when this could be something you wanted, like maybe you had a categorical variable with lots of categories. For example, maybe it's different states in the US. But most often, if you see something like this, lots of different possible coefficients being estimated for a particular variable, perhaps that wasn't really supposed to be a factor variable. Perhaps it should be a number and you're not handling it as a numeric. Similarly, when you look at the ANOVA output, what you see here is that the degrees of freedom are something very different than 1. So there must have been 32 different possible values of REM sleep. So the degrees of freedom here is equal to 32 minus 1 is 31. This is the place to check. If you are trying to make sure that the variable you have, if it's supposed to be continuous, really is being handled as continuous in the linear model that you're running. If you're looking at the ANOVA output from that linear model, the degrees of freedom should be 1 here if it's handled as continuous, and here that's not the case. So avoid that. Make sure that if you have a continuous variable, you actually handle it as continuous. But the problem also goes the other way. If you have a categorical variable, it's a mistake to handle it as continuous. I think this is a more common error. You'll often have a variable in a data set that's categorical, but the values are labeled 1, 2, and 3. And if you read those in as numeric, R is going to assume that's a numeric variable as opposed to a categorical. So to show you what could happen here, I'm going to create something called vor as num, which is going to be a numeric version of the vor variable. So remember that the vor variable is categorical. So if I do this, I can make a table. So instead of now labeling carnivores, herbivores, omnivores, etc., I'm just calling the same categories 1, 2, 3, 4, 5. I can summarize this now. Now here's where you can tell that this numeric version of vor is different than the factor version. You can't take the mean of omnivore, carnivore, etc. But if I start using the labels 1, 2, 3, 4, 5, now I can take the mean. And that's not good here because these are arbitrary labels 1, 2, 3, 4, 5. I could have called them 5, 4, 3, 2, 1, and it would be just as meaningful. So these numbers don't mean anything: the max, min, the median, the mean, and yet it's possible to calculate them if I haven't turned this variable into a factor. Right, so if I summarize the original vor variable, this is what it should look like. It's a categorical variable. It doesn't make sense to take the average of labels that I might put in these numbers. And we can just do a check that we did this correctly. In other words, we do indeed have 5 different numbers that correspond to the 5 different possible labels. So what happens if this variable is handled as numeric, even though it should be a categorical variable? I'm going to show you both the regression output and the ANOVA output. Okay, so what we see here is, even though we know this is a categorical variable, when you look at the regression output, you're only seeing one coefficient. You're seeing a coefficient for the slope of a line where the x-axis is equal to these numbers 1, 2, 3, 4, 5. And that's not appropriate here. What I would rather see, what's appropriate to see, is separate coefficients for all but one of the different possible levels of the vor variable. Similarly, when I look at the ANOVA output, I can see the degrees of freedom is equal to 1. What I expected to see was 5 minus 1 is 4. So this degrees of freedom for a particular predictor is often a really good place to check that a variable is being handled as numeric or categorical appropriately. I want to show you that if I make a plot where the x-axis is this numeric variable of vor and the y-axis is log sleep, right? These are the labels 1, 2, 3, 4, 5. And then if I put on the line that results from incorrectly running this regression with vor as numeric variable, it does indeed draw a line. R doesn't know what your context is. It doesn't know this is really a silly thing to do when this means carnivore, this means herbivore, this means omnivore, etc. R doesn't know this is ridiculous, so it'll draw the line anyway, but the slope of this line has nothing to do with any sort of research question that you might be asking. If the variable is actually categorical, you need to make it into a factor before you put it in either your ANOVA or your regression, or else the results aren't going to make sense.